So, well, I mean, Leo, we are all happy to introduce Leo, especially me. So Leo was some point visiting the UCSD. That's when we worked on geometry and encryption. So Leo worked on a range of topics from more applied lattice cryptography things to algorithmic and mathematical problems in lattice cryptography. He's Simon's research fellow here at the Institute, and he has a position at the CWI Amsterdam, where he's been doing some great work on the mathematics of lattices and algebra. And in this talk, he'll be telling us about the quantum cryptanalysis of algebraic lattices.
Thank you, Daniele. So the official title of the talk was Classical and Quantum Cryptanalysis. I was too lazy to ask the title to be changed. Most of what I'm going to talk about is actually just a quantum cryptanalysis. But I'm putting quantum in parentheses because I'm essentially not going to cover any quantum stuff. I'm going to essentially use them as black box for certain subproblems. I might mention them very quickly. So pretty much we're just going to do cryptanalysis of algebraic lattices and even more specifically ideal lattices. Okay, so why do we care? We care because we're doing lattice-based cryptography. As we've seen yesterday and the day before, lattice gives a great, very strong foundation to post-quantum cryptography because we have those worst case to average case connection, those problems, SIS and LWDs that are very convenient to build crypto system upon. They can be shown to be as hard as the worst case instances of the approximate SIVP problem. So from a security perspective, the question is how hard is this approximate SIVP problem? And it all depends on what is the approximation factor. So in all the algorithm, I think we've seen pretty much all those algorithms on Monday. So we've seen this LLL algorithm from Lenstra, and Lovas, who run in polynomial time and gives you an exponential approximation factor. The story is quite funny because, I mean, at the time where LLL was invented, computers were not very powerful. And when we were running LLL, it will always find something so short that it felt that it was the shortest vector. It didn't feel like the approximation factor was exponential. So the constant hidden in this LLL is kind of so small that you start seeing in already quite large dimension. But still, it is exponential. And on the other hand, we have those perfect SVP algorithms that run in exponential time or even super exponential time. And in between, we have those BKZ algorithm, which is basically making blockwise call to the exponential algorithm, but in smaller block size. And that gives this perfect trade-off from the exponential time algorithm to the polynomial time ones, where we have up to the log factors in the exponent, the product of the approximation factor and the running time in the exponent, this product is constant equal to 1. And the good news is that the approximation factors that are underlying cryptographic schemes, they're polynomial or quasi-polynomial. So they're in this region where the problem seems to be very hard to all known algorithms. Namely, it takes exponential or slightly, very slightly sub-exponential time to solve. So that's great. It's very secure. The problem is that cryptography is not just about security. It's a trade-off between security and efficiency. And here we don't really have efficiency because the key size are kind of huge. We need key size that are quadratic in the security parameter. And in practice, it really hits you very badly because n is in the 1,000, and for each matrix entry you need like 1 or 2 bytes. So we're talking megabytes. And that's not the kind of size we want to talk of when we do cryptography. So to escape this, I mean, I'm rewriting history backward because maybe this is not how it was invented, but a solution to this was to use this ring structure where we replace arbitrary lattices by lattices that we construct as modules of a number field, for example. So here it's not exactly a number field, it's a ring that's not perfectly integral, but later came better rings. But if we do this kind of construction, we get the same lattice dimension, but we reduce the key size to linear or quasi-linear. This construction was completely heuristic. I mean, completely. It was heuristic compared to the more modern things that we do with worst case to average case connection. But a variant later came with this worst case to average case foundation, and they were entitled the ring-cis and the ring LWE problem, or for a short while, the ideal LWE problem. And we have this same structure for cryptography, where we can show that those problems are as hard as a worst case problem, but this time, instead of approximating a short vector in an arbitrary lattice, you have to do this in an ideal lattice. This is applicable in particular for those cyclotomic rings that we really like, because they're kind of efficient. Geometrically, they're also quite nice. I think geometrically they have nice properties. And in those cases, we have this parameter m that tells you, well, this ring is generated by a primitive mth root of unity, and in that case, you have that its rank or its degree is the Euler quotient of m. So I might call m the conductor during the talk, and n the degree or the rank of the ring. So the question is that are those lattices as hard as regular plane lattices, general lattices? And for a while, people were conjecturing that it was the case until a long sequence of results led to show that it was actually not the case, at least with respect to quantum algorithms. But it's not completely devastating. What happened is not the whole line that got suddenly completely destroyed. What was found is that after a certain approximation factor, kind of halfway, exponential of square root of n, suddenly for quantum computers and ideal lattices in cyclotomic ring, the complexity suddenly drops to polynomial. So this is not so devastating for cryptography for the following reason. So in practice, no scheme was actually broken. And the reason is that here I'm targeting this approx ideal SVP problem that is known to be at least as hard as ring LWE or ring cis. It doesn't mean that it is equivalently hard. And in fact, there seems to be, with the current knowledge, actually this reduction seems to only be one way. And the other reason is that, even if it was the case that we had the equivalence, the approximation factors that this algorithm targets are too large, at least asymptotically, to threaten actual cryptographic schemes. But still, it's a new cryptanalytic tool, and it's going to open new doors, especially explored by Alice more recently. And also, it really shows that those ideal lattices are not necessarily as hard as regular lattices.
So this already gives you a break of entry with extreme parameters. It does or not?
No, it's a different attack. The overstretch n-true thing, that's not it at all. It's completely, well, Damien thinks they're equivalent, that there is a reason that things break at the same rate. But for now, I don't think we have any formal connection between those two things. Still, okay, so nothing got actually broken by this attack, but if you can afford weaker assumption, maybe it's a good idea to do it, and this is what we did, for example, with the Kyber scheme that we submitted to the NIST competition. So why such a gap? The idea that I will try to carry over today, more than the details of the attack, is to try to give you a global point of view on what are lattices and what are ideal lattices. So here on those pictures, so they're not real, they do not necessarily correspond to actual lattices or ideal lattices. But let's say that I'm talking about full rank lattices in dimension n. Then one way to describe lattices is to give a basis of it. So that's an invertible matrix. So that's an element of GLN of R. Okay? But there are several bases that can represent the same lattice. Okay? If I can change the basis of the lattice by applying a unimodular transformation. So that is a matrix that is that has integer coefficient and whose inverse also has integer coefficient. So that's a matrix in GLN of Z. So if you want to see all the lattice at once, one way of saying that is to say, well, the set of all the lattice is this quotient, G11 of R over GLN of Z. So GLN of Z is not a distinguished subgroup of G11 of R. I don't know if you remember all your non-commutative algebra. I don't, so I often make mistakes. But it means that in particular, this quotient is not a group. Okay, this is just a space, a homogeneous space, or a moduli space. And this is because we don't have commutativity and we don't have distinguishedness of this. And another bad property of this set, when we think about it, is that it is non-compact. Nevertheless, in this picture, what I want to carry through is that maybe a lattice is the left eye of my little fish, and there are many representative of that lattice, and those are all the left eye of all the fish. And the task of reducing a lattice is to say, well, I kind of maybe reduce it to one fundamental domain of this quotient. Or not necessarily a fundamental domain, because the reduction algorithm that we apply, they don't give you unique representative, but I kind of want to make sure that it lives in a small region of that space. So not necessarily a fundamental domain, but a covering set. And the thing with ideal lattices is that the structure, we can also think of ideal lattices in the same way, and their structure is going to be much simpler. And the reason is that ideal lattices, I can multiply them. I cannot multiply lattices. And this gives you a commutative group. And commutative group, I still have to apply some reduction theory because there are several ways of representing the same ideal lattices, but quotients in commutative group are much simpler. They look like just tiling like this. Okay, so in particular, in some sense, the structure of ideal lattices, the whole set of ideal lattices hide itself some kind of a lattice structure, right?
So Leo,
Yes.
sorry, the change of basis is not necessarily a group element because you're looking at a change of basis as a Z module.
Yes.
So it's lattices. So you're looking at the operation of changing the basis.
Oh, for ideal lattices, I'm being much less sketchy. I'm not telling you I'm speaking of basis, or I'm just. This is going to get clearer where I'm going at near the end of the talk. But
when you say ideal lattices are a group, with respect to what is the operation?
oh, multiplication of ideals. Or.
And that's invariant under.
Under what?
Basis.
Yes, I mean you don't need a basis to define the product of two ideals.
Oh, because it is just as an ideal. Okay, yes, okay.
Leo,
Yes.
this might be a very technical question, so we can take it offline, but are you quotienting by rotations as well on the left? Or no?
You can.
Okay.
You can also do it, and actually, when I'm going to reach the end of the talk, I'm going to give you the true picture of ideal lattices, and I'm going to quotient by rotation, at least k-linear isometries. Yes, you can consider, but you have to be careful when you define it because, I mean, depending whether you use row or left notation, column notation, but you need to quotient by GLN of Z on the right, while you're quotienting by the orthogonal group on the left. So it's even uglier, and I don't know enough non-commutative algebra to make sense of it. I just know it looks funny. More specifically, I mean, I wanted to be a bit more precise about how general lattices look like. You know, you might have seen these pictures several times. So this is kind of a representation of the action of GL2 of Z over you know, the basis of a lattice. So a lattice would be a point. So this is a fundamental domain, this region E2. So a lattice is, you can view it as a point inside this region, but there is an equivalent point in this region here. So you have like those translations. And so that's an easy action of the GLN of Z. But then more complicated stuff happens when you start swapping vectors. Essentially, T is the translation vector where you replace B2 by B2 plus B1. But the swap operation looks a bit weirder. I'm not going to enter this, but I just wanted to justify that non-commutative things looks funny. Okay, so let's go back to commutative things, and let me remind you a few definitions from algebraic number theory.
Yes. Talking about ideal lattices, do you mean integral ideals or fractional ideals?
I even mean slightly more than this. I actually mean, I'm going to complement, I mean, I'm not going to go into those kind of details, but for me, an ideal lattices is just an OK module in the real complementation KR. So you tensor your number field with the reals, and then you can consider OK modules in that space. And that's basically just make your ideal lattices more continuous. Otherwise, you know, all your objects are rational, are described by rationals, and then you don't have the nice continuity that I want to talk about today. So let K be a number field, and OK, it's a ring of integers. And I'm going to consider, so first let me define integral ideals. So that's a subset of OK that is closed under addition, but also by multiplication of elements of OK. And fractional ideals are essentially scaling of the former. And now when I mean ideal, I might essentially mean fractional ideal. And among all those ideals, there is an important class of ideals that are called the principal ones. And those are the ideals that I can describe by giving out a single generator. So that means that the ideal itself can be defined as just being all the multiples in the ring of integer of a single element. So if you think of Z as being the ring of integer we're talking about, then all ideals are principal. But if you go to bigger rings, this is not necessarily the case. In some sense, you do not necessarily have a Euclid algorithm over all rings. I'm going to use IK to denote the set of fractional ideals and PK for the principal ones. It was already covered briefly yesterday, but to view ideal as lattices, I have to give you also geometry, because now by this property we have that ideals are closed under addition, so that gives them the structure of Z module. But for being a lattice, you need to define a geometry as well, and you're going to do this through the embeddings. So we have n embeddings from our number field K to the complex. And we're basically just going to align all those embeddings to define the geometry. So we're going to view X as the vector of all its embeddings. And by doing that, well, we have embedded basically K in the vector space, so we can view our ideals as lattices. And what is nice is that in this embedding space, the multiplication happened component-wise, and it's going to help us understand the geometry that's happening for those ideas in this space. One last definition, I think it's the last, the algebraic norm. So for an integral ideal, we're going to define its algebraic norm as the size of its of the quotient A quotiented by OK. No, that's OK quotiented by A. No, that's embarrassing. Sorry about that. I'm not going to use parentheses because life is short. And this is supposed to be a measure of the sparsity of the ideal A. So the bigger the norm, the less elements it has in some sense. In particular, you can relate this to the volume of A when you are the determinant. I think people call it the determinant when they're a serious mathematician. The determinant of A as a lattice is essentially going to be proportional to its norm.
Can you explain what is OK? Just briefly explain.
Oh, sorry. Okay, for what we're doing, this is a lie, but this is a convenient lie. Let's say that I'm going to define my number field K as being the rationals adjoint a free variable, and then I'm going to quotient this by f of x. So this is how you typically construct. Then I'm going to assume that this is a lie. This is not always the case, but that the ring of integer is essentially going to be those same polynomials, but with integer coefficients. Sometimes it's bigger. Where was it? So yes. So the norm is a multiplicative map. So I can extend it to fractional ideals, saying that, for example, if I can write an ideal as A over B, then the norm is just going to be the norm of A over the norm of B. And I'm also going to define the norm for elements. And this is done by taking this time the product of all the embeddings. Okay?
So X is G there.
Hmm? X is G, yes. And if you do this, then you have a match between the algebraic norm of an element and the norm of the ideal it generates.
An absolute value sign.
Yes, good catch. Thank you. No, there is one more definition. So the class group. So as I said before, we can multiply ideals, and this is in the general setting. This is defined like this. So to multiply two ideals, I'm going to basically multiply the element of each ideals, but this has to be an ideal has to be closed under addition. So what I do is I basically take the closure under addition of all those products. But when I get two principal ideals, I have the property that it remains principal, and a generator of the product of those two ideals is essentially the product of the two generators I started with. So, so by those properties, we have that the set of all ideals form an abelian group under multiplication, and the neutral element is the ring of integer itself, which you can view as a lattice. And the set of principal ideals is a subgroup of all those ideals. So I can take the quotient of those two groups, and this is what's going to give the class group. And maybe amusingly, one of the first properties that was proved using lattices in the history of mathematics is to prove that the class group is actually a finite group. Despite the fact that ideals themselves are infinite, there are infinitely many ideals. And so to write explicitly reduction to the class group, I'm going to use the bracket notation. So basically, an ideal is going to be principal if its class is exactly the class of OK. Okay, so that's a lot of definition. Hopefully you're familiar already with most of this. So what are we going to do with all this? We're going to solve approximate ideal SVP, and those are all the steps that are necessary to do this. So first, I don't like non-principal ideals. Principal ideals are really much nicer. So the first thing I'm going to do is to make them principal, or to translate my problem to an ideal that is principal. And to do this, I'm going to try to solve what I call the closed principal multiple problem. So I'm given an ideal A, and it's not principal, but I'm going to try to find a sub-ideal C that is principal. Because if I find a short vector in a sub-ideal, then I find a kind of short vector in the original ideal itself, right? So, of course, you don't want the sparsity of C to be much bigger than the sparsity of A. Otherwise, you're just not going to be able to find short enough vectors. So you need to control that a little bit. So to do so, the strategy is going to do as follows. I'm going to look at the inverse class of my ideal A, and I'm going to try to write this class using another set of small prime ideals. So I'm going to try to find a representative of the class of the inverse of A. And this is a class group discrete logarithm problem. And those problems are typically classically very hard, but since a few years it is known that using quantum algorithm that this is actually doable in polynomial time. So this is based on the work of Eisentrager, Algren, Kitaev, and Song, who have this generalization of Shor algorithm to continuous group, essentially. And this was later applied for the class group discrete logarithm problem by Bias and Song. Most of those people are here in this room. I'm basically going to let them explain this probably next week at the quantum workshop, and I'm going to focus on the other steps, which are more related to lattices. So once we have this representative, what I'm going to do is to try to make this representative smaller, because there is no guarantee of size given by the output of those algorithms. But by making them smaller, then I will be able to construct my principal ideal C in the following way. And because the x are small and the pi will be small, the gap in sparsity between A and C is going to be kind of controlled. Okay, so I now have obtained an ideal C that is principal. And now I'm going to tackle this. And I'm going to, once again, apply some quantum magic. So I have an ideal that is principal, so I know that a generator exists. And in fact, there exist many possible generators for this ideal. And I'm going to call my favorite quantum algorithm and going to get an arbitrary generator of it. Again, there is no guarantee of size on this generator. So I'm going to apply, I'm going to multiply this element by elements from the unit groups to make sure that this generator is actually small. And I'm going to output this element. This is a generator of C, so in particular it's an element of C. C is a sublattice of A, so I obtained an element of A, and I'm claiming at least that it is kind of short. Okay. Yes, and I'm going to cover those things the other way around. First, because I mean this step was discovered earlier, but I think the ideas are more natural this way. So we're going to start by this step 4 here. We're going to start from a generator G, and we're going to try to make it shorter. Okay, so formal definition, we have an ideal. We have the promise that it is principal, and in fact, we're given this ideal by one of its generators. And what we want is to find another generator G that is smaller. So all the generators of a same ideal, they must differ by a unit, right? Because I'm able to construct G from H and H from G. So it means that their ratio is a unit. So basically, the problem can be rewritten this way. I want to find a unit U such that U times H is small. And by small here, I really mean the smallness with respect to the Euclidean norm that I've defined through the embeddings. And I'm assuming that the ideal is already given by its generator, but when you plug all this in the big machinery for ideal SVP, you have to rely on the principal ideal algorithm by Biers-Sensong to actually get this generator. So I don't like multiplication. It looks scary. So I'm going to transform everything into addition, and I'm going to do this by the logarithmic embedding. So essentially, this looks like a multiplicative problem, and I'm just going to make it look additive. It's not going to change much, but at least we might. It's just more intuitive in some sense. So to define the logarithm of an element, what I'm going to do is to look at its embedding. So remember that embeddings are multiplicative. If I multiply two elements, then all the embeddings get multiplied. So if I want to define the logarithm of an element, I can simply take the logarithm of each of its embedding, and that's going to send something multiplicative to something additive. One thing is that you do not exactly need to do this for all the embeddings because of those absolute values. If you have two embeddings that are complex conjugate of each other, they're just going to give you the same information. So it's kind of useless. So that's why we do this maybe weird construction where we separate, what are called the real embeddings from the complex ones. So that means the one that are kind of self conjugate to the one that are pairs of conjugate, and then we send our elements of our field to this real vector space R to the L, and we obtain a group morphism from the field to this additive space. But it's also, so here, sorry, instead of R, I should have written OK. OK itself is not a group. Okay, if I multiply integral elements, I can do that, but I cannot divide them. But it's still a monoid, and the logarithm is going to preserve that structure as well. And the important idea behind all this is to understand a bit better the structure of the group of units. And this is more precisely stated by Dirichlet unit theorem that tells you that two things. It tells you that first, the logarithm map is kind of faithful. It does not forget a lot of information. So more specifically, its kernel is just the cyclic roots of unity of OK. So there's just a finite amount of them, and typically you don't care so much about them because if something is small and you multiply by a root of unity, it's going to stay small. But the important part of the theorem is the second one, is that the logarithm of this multiplicative group is not just an additive group, it's actually a lattice. So it is not dense, so it is separated. And you can even get its rank. Its rank is going to be L minus 1. Why L minus 1? Well, let's assume, for example, that all the embeddings are real. Then if something is a unit, its algebraic norm must be 1, meaning that the product of all the embeddings must be 1. Okay, so if I take the logarithm, I get that the sum of all the embeddings is 0. So we have these necessary equations on units. So that's why we have to lose at least 1 rank. But Dirichlet unit theorem tells you this is all you lose. I'm going to use this notation H later on as the hyperplane containing my logarithmic unit lattice. And so why have we done this? Well, because now this multiplicative problem where we were trying to find a unit that when we multiply it g by, we get something short, we can kind of rephrase it as an additive problem. Now we're looking for the logarithm, we're looking for a unit whose logarithm plus the logarithm of h is kind of short, because I'm not going to go into the detail, but the logarithm and map also kind of preserve size of things in some sense. But in some sense, I can say that G is small if log of G is small. So now I'm looking for log of G as something short in what is actually the coset of a lattice, right? Because we say that this is a lattice and this is my target. So essentially, we've rephrased the problem as a closed vector problem in a lattice. So maybe it's weird because we started with this problem, I want to find something short in a lattice, and now I've done all those transformations, I'm back to a lattice problem. What's the point? Well, the point is that at the beginning, my lattice was arbitrary, whereas here, the lattice I want to work with is fixed. It only depends on the number field. Okay? And so, yeah, let me get a bit more pictorial about this. So this is how the embeddings of this number field looks like. So my ring of integer here is the adjoint, the square root of 2. And there are two embeddings. Both of them are real, so it's nice because then I can plot it in 2 dimensions without having a complex 2-dimensional board. And I recall you, so my ring, the square root of 2, is the set of all the blue points in this picture. And we have not only component-wise addition between those ring elements, but we also have component-wise multiplications. You might notice that this plot has symmetries. One of the symmetries is just induced by the fact that we have multiplication by -1. That's just going to turn things around. But the other symmetry is induced by the fact that this is not just any number field. This is it has a Galois group. It is a Galois extension. So in particular, the conjugation that sends square root of 2 to minus square root of 2 is going to be a symmetry in this representation. It's just going to swap the embeddings. It's going to send the x-axis to the y-axis and the y-axis to the x-axis. So we have symmetry along this axis. And then I want to bring your attention to 3 kinds of elements, the blue one that I'm going to call the orthogonal elements. So why orthogonals? Well, remember that we have component-wise multiplication. So if I multiply something by an element that is on those diagonals, what it does is essentially multiply each coordinate by the same value or the negation of that same value. So it means that when I multiply by those elements, I'm just getting a scaling and a rotation, but I don't get any distortion. Whereas if you multiply by an element, for example, like this, it's going to, increase things a lot vertically and shrink them horizontally. Another set of elements that are, really central in here are the units. And the units are exactly those elements of the ring, so the blue dots that falls on this hyperbola in red. Remember that the units must have algebraic norm 1, meaning that the product of their embeddings is equal to 1, and that exactly corresponds to the hyperbola of parameter 1. And I'm also drawing those isonorm curves. So basically, those are elements that have the same algebraic norms lives on this same curve. And why do I draw this? Well, because when I multiply something by a unit, I'm leaving the algebraic norm invariant. So it means that when I'm looking for a short generator, when I multiply an element G by a unit, I'm kind of stuck on one of those hyperbolas. So now this is what it looks like when we start taking stuff to the logarithmic embeddings. And this is just done by taking the logarithm of each coordinate one at a time, and it might come as a surprise that suddenly all those hyperbolas becomes nice straight lines. So now so we have, recall that we have a multiplicative monoid on the left, and basically if we take the logarithmic embedding, we get an additive monoid, meaning that here I could multiply point coordinate-wise, and this corresponds to adding them in this space. But I'm not allowed to divide on the left pickers, meaning that here I'm only allowed to add points, I'm not allowed to subtract them. So that's why we get this kind of asymmetry where there's a lot of things to the right, but not much things to the left. And there is this particular sets of units. When I take the logarithm, I obtain a lattice. So all the blue points on the red line. And it is orthogonal to the 1, 1 vector because of this norm constraint that the product of the embeddings is 1, so the sum of the logarithm is 1. Now if I look at the elements that live not on the red line but on any other of those orange line, what I see is that I always get shifted finitely many shifted copies of the lattice that lives on the red line. And this is just because of the monoid property. If I have a point on the red line, on an orange line, I can add the points that are on the red line, and that gives me a copy of the whole lattice still living on this line. It can happen that there are several copies or no copies at all on each of those lines, but it doesn't matter so much. What is important with all this is that I can reduce using my lattice. Okay, I have essentially the points on each of those copies of the lattice. They're representative of a principal ideal. They correspond to one generator of it, and by multiplying by units, I obtain other generators. And I want to reduce modulo the units. And in the additive setup, this is very easy to do. This is something we're very familiar with. We just want to reduce modulo a lattice. All we need to do this is a good basis of that lattice. So this is why we're kind of taking those logarithms. There's just one or two bases of that lattice. So because here we're in dimension 1, that's kind of, there's just one way of doing it. But basically it means that by subtracting or adding the right number of elements of OK, I can always bring a point back in that strip. Okay? And that strip lives in the logarithmic embedding, but what it means in the original embedding is that I can always make sure that my generators lives in this cone. And remember that we were stuck on those isonorm curves. So if I want to make something short, I cannot make it arbitrarily short. I'm stuck on this line, and basically the best way of making it short is kind of trying to make it as close as possible as this blue line, right? This is where my hyperbola is getting the closest to the origin. So this is the general strategy. So now the question is like, can you implement this strategy in general? I mean, you need to know your lattice of units to do this, and you need a good basis of it to be able to do this efficiently. And it turned out that for the case of cyclotomics number fields, so I'm specializing here, that this is actually very easy to do because for cyclotomics units, we know a lot of units very naturally. They're very easy to write. In the general case, if I give you an arbitrary number field, computing units is not an easy problem, or at least if you don't have a quantum computer. But in the case of cyclotomics, it's, they kind of pop out. You can write them by hand. You don't even need a computer. And what is nice about this is not only you don't need much effort, is that you can also study their geometry, and you can actually realize that those units that are kind of naturally given to you, they actually form a rather short basis of the logarithmic lattice. So basically they all have lengths about square root of m or square root of n. It's proportional. So the thing is that you kind of want to obtain a closed vector, but not for the L2 norm, but more for the infinity norm, because it's the kind of norm that goes well through the logs, because the logarithm is done component-wise. So if, you can kind of see why when you take logarithm of exponential component-wise, you kind of want to work with the infinity norm. So you cannot just use the algorithm we've seen for the closed vector problem, where you just take a a fundamental region given by the basis or by the Gram-Schmidt basis. This is not going to guarantee what you want, but if you randomize that algorithm a little bit and try a few times, after a while, after a polynomial amount of trials, you're actually going to be able to solve the closed vector problem in the infinity norm, and you're just going to lose a log factor on the approximation factor. So that's kind of where the square root of n in the exponent comes from, because I've done all this in the logarithmic space. So now I'm going to take the exponential back, and that's what's going to lead to this exponential or exponential of square root of n or quasi square root of n approximation factor, which is in the exponent, basically because I'm reverting the logarithm.
Leo, I'm
Yes.
sorry to interrupt. Could you go back to what's randomized about the CVP algorithm?
So what you can do is Gaussian sampling, and then you can do Gaussian sampling with a variance of square root n. And in each direction, you're going to have a variance of square root n, and if you're lucky enough, no direction will be greater than square root times time log n out of n directions. I mean, you don't have to do as complicated as Gaussian sampling. You can simplify the algorithm and make the analysis more painful. It's really, I mean, this is all standard. There's no fundamental difficulty here.
Here's that you're solving, you want to solve it in the infinity norm, but you're solving it in the L2 norm, so you use randomization to like hope to get something that's good in the L infinity norm.
Exactly. Yes. Yes.
Also, it's essentially the orthogonal lattice, this lattice. So just rounding the coordinates give a good intuition on what happens.
Pardon?
It's also essentially the orthogonal lattice.
It's a rotated orthogonal lattice.
The rotation matters because the L infinity.
Yeah, for the infinity norm, the rotation counts a lot. Okay. So I guess I'm done with this part. More question before I move to the second part? No?
Or just quickly, this final term, you can't end up in a case where the norm of the generator you're given, the norm of H is so bad that this actually affects, that this is actually a meaningful factor here.
Sorry, come again?
This final term in the bound of the length of G, you can't get a case where the norm of the original generator is so bad it actually affects it.
Okay, so remember that when we're trying to find something short, it's always relative to the volume of the lattice that we're talking about. And this algebraic norm that you have at the end, you remember that it is related to the volume of the lattice. So essentially, this quantity that you see before here is the approximation factor, whereas this one is kind of your target. So okay, so multiplicatively, you've lost this factor. So far, so good. Okay. So the second part, the closed principal multiple problem. So now we've assumed all so far that the ideal that was given was principal, and now the question is how do I generalize this to non-principal ideals? And the idea is to just make it principal, or at least find a sub ideal of it that is principal. So you can rewrite this as follow. I'm given an ideal and an approximation factor f. But this is not in the same sense than before. And what I have to do is to find a small integral ideal b, such that this product has the trivial class, such that this product is principal. And I want the norm, the algebraic norm, this time of b, to be smaller than this approximation factor. So now I want to find a subideal of an ideal who's where I'm not losing too much sparsity. And to do so, well, you're not going to look for any ideal. You kind of need to restrict kind of your search space. So you're going to choose a factor basis. So you're going to choose just a set of, well, not even necessarily prime, but let's assume they're primes. Prime ideals, And I'm just going to try to construct a B with the properties that I want, which is going to have this form. It's going to be a product of over this this set of prime. And if we if the elements of B are small and my exponents are small, then I can hope that B is small as well. So before trying to find a short solution, let's try to just find one solution. And essentially, that's a discrete logarithm problem in this class group. I'm given a few generators of my class group, and I have one particular class, A-1, that I want to represent. And so this kind of problem, again, was a few years back proved to admit quantum polynomial time algorithm by Bias and Song. This is not exactly how it is stated in the papers. They have a much more general statement, but we can specialize it to the class group discrete logarithm problem. So that gives me a solution to this equation. I want the product of A times B to have the trivial class, but I have two problems with this solution. The first one is that B might not be integral. If I have negative coefficients in this exponent, then I'm not going to get an integral lattice here. That's going to be somewhat easy to solve, at least in the case of cyclotomics. The second problem is that the algebraic norm of B is going to be exponential in the L1 length of E, and that may be huge if I just use the output of the Bias-Song algorithm. Actually, what we want to make everything fit nicely together is an L1 norm of E that is n to the 3 halves. Why is the L1 norm? Well, because when I take the product of all those things, I'm just basically going to multiply all the elements. That means adding all the exponents. And then I can upper bound the sum of all the exponents by the one norm of the exponent vector. And I kind of want all these elements to be, all those exponents to be positive anyway. So actually this L1 norm is exactly going to give you the measure that I want. So one way of thinking about this problem is to think of the Cali graph of the class group, which I think I've hidden in under here. Yes, it's can show. Yeah, you can read still. So I view my group. I construct a Cali graph as I'm given a group G, and I choose a set of generators A, and I'm going to draw arrows between elements when multiplying by A, since from G to GA. So for example, if I take the additive group modulo 5, and I take as two generators 1 and 2, this gives me this graph. And kind of the question that we're trying to solve here is that we're given an arbitrary point in this graph, and we're trying to find a short path back to the origin, okay, the trivial class. We're trying to find something to multiply by so that the product is the trivial class. So we're trying to find a short path problem. And the good news is that, there's like, if you take enough ideals, enough prime ideals in your factor basis, is that this graph is kind of an expander. There exist very short paths from anywhere to anywhere. The thing is that this graph is the exponential size, so it's not like you're going to visit, it's not like you can easily find this path. And once again, to solve this problem, we're just going to translate it as a lattice problem. One other way of viewing this thing is to consider the kernel of this map. I didn't write the map. So basically, I take an exponent E, an exponent vector E, and I'm taking the class of the product of the pi to the E, or the underscore should be on the P. Sorry. But basically, I'm considering all the exponents, and I'm looking when does the exponent the vector of exponents send me to the trivial class. And that's a lattice, right? Because z to the b is an additive group, and the class group is multiplicative. So basically what I've done is translate my graph problem into a lattice problem. And I mean, you can also view Zn as kind of an infinite graph, right? I'm drawing arrows for, horizontally and vertically that correspond to, adding the generator 1 and generator 2 in Zn. And then if I look at the kernel of this map, I actually get a lattice. And it's kind of like there is a morphism from this infinite graph here to the finite graph here. Okay? And the kernel of that morphism is exactly the lattice of class relations. So if we rephrase this like this, I get a class, and this class is a lattice coset. So that's a point modulo one of those fundamental cells of the lattice. And sorry, like this. So basically, yes, one target, a class is just one of those points, and all I'm trying to do is to find a short path to a point of my lattice, so a point that is circled in red. I mean, this is exactly a closed vector problem, right? Because if I find a close point here, then I have my path. It's a kind of a Manhattan graph. So things are closed, then the path is easy to find. So that's it. We've pretty much rephrased our problem as, once again, a lattice problem. The question is that, again, in general, what is this lattice lambda? And this is, in all generality, very hard to compute for an arbitrary number field, and even more so for an arbitrary basis of, for an arbitrary factor basis. So in some sense, the question is, why should we know anything special about the lattice lambda that would allow to solve this problem? And again, the magic happens in the case of cyclotomics. We have this beautiful theorem of Stickelberger that would take me too many slides to formally give you. But essentially, for a cyclotomic number field, this lattice of class relation is very well known, very well understood. We can describe it completely explicitly. And in fact, we can even explicitly give a short basis of that lattice. That means that we're going to be able to solve this closed vector problem, and it's going to fall exactly within the approximation factor that we are hoping for. So putting all this together, we're able to solve the original problem of finding a closed principal multiple.
Does this L1 thing give you trouble just like the L infinity thing gives you trouble, or it just doesn't matter here?
No, it's much easier. Yes, because
basically,
yeah, I guess on average the L2, L1 bound is pretty tight. No, so here you don't have to fight against this. Yeah, you just. Is that all? No, yeah, I've hidden a lot of ugly stuff to you. So one of the difficulty is that for applying Stickelberger theorem, I kind of want to take a prime ideal and all its conjugate, but it is not necessarily the case that this generates the whole class group, so it might be that you kind of cannot reach all the elements of your class group in this way. It is okay. We can actually live with needing several elements, just a constant or a small polylog, a number of elements generating the class group. The other difficult part is eliminating negative exponent, because if you have a negative exponent, that completely screws up your strategy, because then the ideal that you're constructing is not integral, meaning that the product with your original ideal is not going to be a subideal. It's going to be somewhat unrelated. So you really need to make sure that all the exponents are positive. One way you can do that is because, at least in the case of cyclotomics, or often in the case of cyclotomics, if you take the conjugate, the complex conjugate of an ideal, then its class is exactly the same as the class of the inverse of the ideal. So you can basically transform negative exponent into bars. It's kind of cyclotomic magic. I'm not going to enter into those details.
Sorry.
Okay. Yeah, sure.
One more time. Who's BPR04? This is the citation.
I don't remember. It's been a long time.
Oh, sorry.
It's all right. I should know. Yeah. Buller, Pomerantz, and Robertson.
Okay.
They kind of yes, they relate this to crazy variants of the Cohen-Lenstra heuristic.
Okay.
Don't ask more, please. So yeah, just a few words about the quantum set I've hidden so far. So it's based mostly on the continuous version of this hidden subgroup problem that was solved 6 years ago by Eisentrager, Hallgren, Kitaev, and Song. This originally was applied only to the computation of the unit group, and with some more work it has been generalized by Bias and Song to solve the principal ideal problem, so that is finding a generator of a principal ideal, but also solve those class group discrete logarithm and even more general. I mean, if you abstract things enough, all those things are kind of the same problem. And that's the formalism they use using S units. And more recently, we proposed a refined complexity analysis of the continuous hidden subgroup step. But there are still, so because it is only announced to be polynomial time in those works, and we, for cryptographic concern, if there is a cryptanalysis that is polynomial time but is n to the 25, that might not matter so much, especially on a quantum computer, or at least maybe not tomorrow. So we wanted to have a better idea of the refined complexity of this algorithm. But there's a lot to do, and we did not answer this question for all the steps of the algorithm. So we left a lot of open questions. You might be unable to comprehend them without more information, and that's the purpose. I want to frustrate you so that you go read my paper. But wait for a few more days, because we're still updating it, so it will be on the print very soon.
Can you give a spoiler of what the complexity is?
There's like so many parameters. The thing is that, I mean, when you look at the definition of the continuous hidden subgroup problems, there are many parameters. But essentially, if you just look at just the dimension of the ring, so n, this generic analysis tells you at least n to the 7, ignoring other parameters. But there are many reasons I think it can be improved, because like the algorithm is completely generic, and there's like some of those questions here are pretty much, if you specialize things to cyclotomics, how much can you gain? I think there is a lot to gain. It's like even before going to the non-generic version, there are still some steps of the algorithm that are not analyzed in our work. In particular, you need to construct a quantum periodic oracle from which you're going to extract the hidden period, and that's what those algorithms do. And we do not analyze the construction of this oracle in our paper. We really just analyze the period extraction part of the algorithm. So I think this is a goldmine of open problems, and I think this is the right workshop to crack them up. How much more time do I have?
20 minutes.
20? Okay. So I want to mention a few further works and ongoing works in this line that, and It's not necessarily cryptanalytic, but it goes in the same framework. So the first one is some work we published last year. What's a bit frustrating, again, I like bigos, but I also don't like them. So I first use them, and then I say, but what's the hidden constant? And in all the analysis that I've given you so far, I was hiding a lot of bigos, meaning that even if we could say that, okay, asymptotically, those attacks don't really matter for cryptography because the approximation factors are just too large. The question is like, yes, but in practice, there's so much hidden behind those bigos. How can we explicit what's behind the bigos and know for real whether those algorithms matter so much or not for practice? So we've done that with Plançon and Wesolowski. So here, for example, in the blue line, you have the approximation factor or the root approximation factor that is reached by the naive implementation of those algorithms. And then we kind of like, because we were in those original paper, we were just interested in bigos. We didn't do much effort to try to improve what's behind the bigos. And so we do that here, and we're able to improve the algorithms significantly. And this is the approximation factor we kind of reach. And then there's like those two lines, and those two lines are like things that we don't know how to do in practice, but we have an argument to say that this is a lower bound of what a certain class of algorithm within this range could achieve. I'm not going to be more precise than that, because of course lower bound does not exist before we prove P different from NP. So it's a very restricted class of algorithm I'm talking here. And then we compare this to, the usual algorithm that we apply to try to break cryptographic schemes. So for example, LLL or BKZ with larger block size. So LLL is, it's polytime. It's something I run every day on my computer. Well, not if the basis is too big, because it is polytime, but it is very painful to parallelize. But let's pretend it's an easy algorithm to run. So, even LLL, it would require you dimension 4,000 to beat LLL with your quantum computer. And that's with the naive algorithm. But with the improved one, we've decreased that to 1,000. But in cryptanalytic context, beating LLL is not what you need. You need to beat much more powerful algorithm. For example, if you want to break NIST candidates, they typically are secure up to, they're set up to resist BKZ 300. And the quantum algorithm, even the improved one, is not beating BKZ 300 before dimension, what is it? 2 to the 14, 8,000 or 12,000, something like this. Yes. This is the root Hermite factor. Yes. Yes. So that's why it's a straight line for all those algorithms, because basically I've chosen the scale so that those algorithms have a straight line, and because they have exponential approximation factor, but the constant decreases as we increase BKZ block size, whereas those one have a sub-exponential approximation factor. So that's why we see those lines decreasing. Yes.
The approximation factor you show here is after the two steps.
After the two steps of the algorithm.
One step that is better than the other, like are they comparable? Are they increasing?
Asymptotically,
but when you
asymptotically, I think asymptotically the class group step cost more. In practice, the unit group cost more. So I also wanted to mention this work of Enrose, Télé, and Alice. It was published last year. So this time they're like, yeah, cyclotomics, that's just too easy. What's happening in the general cases? But they're gonna they're helping themselves. They assume that basically they can do an arbitrary precomputation that only depends on the number field k. So somehow this is non-uniform algorithms for from a complexity point of view. And then basically they generalize the result to any number fields. And they also are able to actually obtain a full trade-off and not this brutal drop. So somehow the situation is even improved, at least in the non-uniform setting. And you see, I'm not sure how accurate this picture or how fair this picture is, but it means that the algorithm might kind of hit crypto just a little bit. At least if you take like the most extreme variant of fully homomorphic encryption that have very large approximation factors. I mean, in theory they have quasi-polynomial. In practice, it might be in the range where Alice algorithm actually improve things. But again, that's only for ideal SVP and not for the ring LWE problem that we actually use in crypto. So
when you say fully homomorphic encryption, you mean Craig's fully homomorphic encryption?
Our Craig's is completely broken, but because this is parts of the CDPR paper I did not cover. So here I discussed the worst case part in CDPR, whereas to break Craig's original scheme, the target is not worst case. No, because you sample. So what happens is that you sample the ideal, the principal ideal. You sample it by sampling its generator. So the generator itself is a spherical Gaussian. But when you take this to the logarithmic embedding, you actually end up in a small region of space. And so basically you end up with a BDD instance in the logarithmic embedding. And actually the really hard part in CDPR, that calls all those L function and all that, this is related to this part of the result, to the case that you show that you can solve BDD instances. Because when you want to solve those BDD instances, you have to look at the dual basis, and then you have characters that pops out, and suddenly L functions are in the picture. So that's the funniest part of the result, but that's kind of the one that lived the shortest, right? It just broke that scheme, and now.
Sorry, break in what sense? In quantum.
It's like you give me the public key, and I find the secret key.
I know, but break in quantum polynomial time.
Quantum poly time.
This is actually going to break as a worst case to average case reduction in a crypto paper, if I remember right. Which says, if you break a scheme, you solve a worst case problem. Now,
no, it does not apply to a scheme.
Sorry?
It does not apply to a scheme. Does it?
I think so. That was the point. That was really the point.
So we've read that paper together, huh?
We can take it offline.
Yeah, because I'm also going to talk about a new worst case to average case reduction. Okay,
offline.
Yeah. Okay. Okay. So now I want to introduce. Yes.
And a comment on the previous one. So, yeah. So it doesn't really impact crypto. It only impacts the justification of ring LWE.
Yes.
Hardness of the potential hardness of ideal SVP.
Yes. Yes. Okay. So. So the thing is that what we've done so far, I mean, if you look at the two steps of the algorithm that I've discussed, they kind of really look the same, right? It's like each time we had to find first a representative, and then we did some lattice reduction to reduce it. Each one time we took a continuous logarithm, and the other time we took, discrete logarithm in the class group. And I mean, you can live with that and say, oh, it just looks the same, or you can say, well, if it looks the same, probably mathematicians have a way of speaking of both things in common terms. And this is what Arakelov theory is for. And I want to use the 10 minutes to introduce circular theory. That's going to be a way too short introduction. So those two things are exact sequences. So in an exact sequences, you have that, so by each arrow, I mean that I have a morphism. And an exact sequence is when the image of each arrow is exactly the kernel of the next arrow. And those, those exact sequences with exactly 3 elements and the trivial groups up there and down there, I think they're typically called short exact sequences. And one way to interpret short exact sequences is to, if you say one way to interpret this exact sequences is to say, well, C is actually or isomorphic to B quotiented by A. Okay. It does not necessarily imply that B is a Cartesian product of, less than A times C. This is not necessarily true. Okay. And, okay, so what have we done? In the first part, so remember, H was this logarithmic embedding space. And using the logarithm map, I was sending all my units to what was a lattice. And so basically, I can define T as the quotient of the space H by the logarithmic. I'm just going to call it lambda. There's the logarithmic units. And essentially what we've done in that step is to say my target is a principal ideal, and so I can view it as an element in that torus. And I'm first going to try to find one representative of it in H, and then I'm going to use the units to make this representative shorter. Okay. And in the second part of the talk, we've done exactly the same thing. We had one particular class. We used our quantum algorithm to find a representative of that class being an ideal. And then we used relations in the class group. And relations in the class group are just principal ideals to reduce the representative of our class. And somehow, what's tempting to do is to try to construct an object that lives between those two things. Somehow, two important objects that we were dealing with were the class group and this torus, and we kind of like to construct an object that kind of combine both. So it would be tempting to say, oh, what I want to work on is T times maybe the class group, the torus, times the class group. This is not what you want to do. Somehow, if this is what if the picture should look like this, it would mean that the class group step and the torus step would not interfere with each other. But this is not the case. And this is particularly visible when you look at the work of Alice, because she kind of implicitly already does hierarchical theory. She constructs one bigger lattice that mixes the relations and the units. And she does it by taking log of OK first, and by constructing a basis that's looking like this. Log of OK star. And then she takes like class relations here. And for each of those class relations, there is a principal ideal associated with it. And she chooses a generator of that principal ideal, and she puts the generators here. Okay. And when you look at this at this, it means that somehow those generators make the two objects interfere in some way. And if we were to want to look at this object, it would mean that the generators here would be 0. Then we would have kind of a diagonal structure, and that would correspond to this direct product. So how do we actually construct the right object? Well, we're not going to construct it directly. We're going to take a small detour here. So the first thing I want to do is to say that H, so that was the logarithmic space, and that space just looked like the sum of the real over what I'm going to call the places, or more precisely, the infinite places of my ring. If you remember, in all my embeddings, there were pairs of complex embeddings and real embeddings, and I didn't wanted pairs of complex embedding to be counted twice. And when that corresponds to places, to infinite places. So this is basically, this is R to the L, except that I'm kind of giving a name to each of those coordinates. Now, ideals, sorry. So this is a multiplicative structure, and I kind of want a basis of this multiplicative group. What is this basis? The primes, by the prime ideal theorem, right? Any ideal can be written uniquely as a product of primes. So it means that this multiplicative set of ideal, I should be writing it like this, Z, where P prime. Okay. So this is very large. Huh? There is like infinitely many coordinates, but I'm only allowed integer coefficients. So that I'm going to call the finite places. I mean, I say I, but I mean, of course, I'm talking about centuries of mathematicians. Finite places, and those are infinite places. And so all I want to do is to first construct something that's just going to be all those places. So, and I'm going to call this the divisor of the number field K. And I do have this structure, and in particular for the set of divisor, we actually, I think this is simply a direct product here. So I have construct something in the middle. Those are exact sequences, but I don't want to write the zeros to the left and the right because I don't have enough room to do that. Yeah, now I'm going to try to complete this whole commutative diagram. So on the top, what's happening? So we have the units here. I mean, we have to forget the roots of unity because they're always annoying. And we have principal ideals here. And if we remember, you know, a principal ideal, you can view it as an element of the field modulo units, right? Because if you change a unit, that generates still the same principal ideal. So what you can do is to write another arrow here. And here you're going to have the field itself, K star. I'm removing 0 because is 0 a real ideal or not? That's a difficult question. I'm going to assume it's not. Okay. And so, yeah, maybe I should have given the formal definition of div of K. I mean, this is just a direct sum that we have here. Okay, so a divisor is just an element of this big group here. So this is over the places, the finite places. So, I mean, a divisor is just like a stupid formal sum of stuff, right? And I'm going to be able to construct an arrow like this by sending an element alpha to what we write like this with strange parentheses. And this is going to be, I kind of need to evaluate alpha at all the places. So on infinite places, we know how to evaluate alpha. We just, take its log embeddings. So it's just going to be the sum for all the infinite places of nu of alpha, and I'm going to take absolute values and log around that so that the multiplicative structure is sent to additive. And the other thing I'm going to do is I'm going to write the ideal generated by alpha. So, okay, yeah, can you see down there? I'm going to write it as a product of prime ideals. EI. And that's going to give me the finite part. It's the sum over all the prime ideals of... sorry. I need to add a special symbol nu here. This is a formal sum, so I need a special symbol for each of my basis elements. And EI. That gives me an arrow from here to here. So now I have an arrow from here to here. So what can I do? Well, I can define a quotient. And this quotient is called the Picard group. And then I'm thankful for Kuhn to teaching me about this magic lemma called the 9 lemma that tells you that when you have these pictures, actually those arrows exist and the diagram commutes and all sequences are exact. And I'm not going to prove it. So why do we care? Well, first, it looks nice. The Picard group, we've had this exact sequence where on the left we had a torus and on the right we had a finite group. So it means that kind of the Picard group looks like a bunch of donuts. Okay. This bunch of donuts does mean something. So the Picard group, actually, if you do some more work, you can realize that it corresponds to the set of ideal lattices, modulo scaling isometry. So this is really an object we want to look at, right? We are looking at all the ideal lattices from a global point of view. Each point in this group corresponds to an ideal lattices. Meaning that if we want to understand how ideals relate to each other, we want to view them in that group. And this is what we're currently doing with Kuhn and Alice and Benjamin. The main theorem that we're proving is that if you do a short random walk in the Picard group, I'm not going to define what it means, you're very quickly, after just a few steps, you become uniform inside the Picard group. Okay, like this, it doesn't sound maybe so important. Actually, you can deduce a lot of application out of this theorem. The first one is that you have random self-reducibility of the ideal SVP problem. Essentially, this random walk is going to allow me to send the problem over any ideal to a random ideal in the Picard group. So that's a worst case to average case reduction, right? And it doesn't look at all like the one that we have had so far. But what is funny is that it looks very much like the self-reducibility that we know for discrete logarithm over elliptic curve. There's this result of Benjamin that says that you can randomize an elliptic curve inside an isogeny class, and this is exactly the same strategy. But we have other applications. We can eliminate some of the heuristics of the previous result of Alice. And we can eliminate heuristics. So those, you can, this one you can understand as the heuristic. Once you speak in the language of the Picard group, you can understand a heuristic as basically saying that the radius of the Picard group is not so large. And because we just say that a random walk takes you uniformly, it means that a short walk takes you anywhere. So this radius is kind of small. And then we are able to eliminate heuristics maybe in other contexts, which might seem a bit stranger. Why would that relate? If you're interested, we can discuss it offline. But basically, these theorems can help you to prove that when you sample an element in an ideal, then the relative norm of your element to your ideal is maybe easy to factor, or is smooth or near prime or something. So we can do this at least for for some algorithm that Kuhn has been working on for a while. We're also hoping maybe later that we can apply this strategy to proving the sub-exponential algorithm for the PIP problem of the unique or class group computations. I think I'm way out of time.
So one question.
Yes.
So one difference between the worst case average reduction for lattices and random self-reducibility is that in the lattice setting, you lose something in the approximation factor.
Yes.
So are you saying that you can do average case to worst case preserving?
No. I'm losing something, and I'm losing an approximation factor that's going to depend on the length of my walk. So that's why I want fast randomization. Yes.
How does it compare to Gentry's worst case to average case reduction for ideal lattices?
We're still analyzing that. I mean, for sure, his reduction requires a factoring oracle. So we don't. I mean, our reduction is classical, and his is either quantum or super polynomial. The exact numbers I don't know. I mean, it also differs in the sense of the distribution of what we mean by a random ideal. His distribution is only considering integral ideals, and is taking a random integral ideal within. It's not even uniform, but it's like inversely proportional to its norm in an interval of norms. We're doing uniform in Picard group. Maybe to cryptographers it doesn't matter at all. I think mathematically it is much more meaningful because of these properties that the Picard group is exactly the quotient of, it's exactly the space of all ideal lattices.
What's that last line? Elimination of the heuristic unique / class group / PIP computation.
That's what I mentioned, that I'm hoping that this kind of techniques will help you eliminate some of the heuristic of the algorithm that you've been working on a lot.
Yeah, but I guess what I meant was what...
Which heuristic? The heuristic that when you take an element in an ideal, then the relative norm of that element to the original ideal, that it kind of behave randomly. Because you want this, you want this relative norm, you want it to have a relatively smooth norm, for example. You want it to be easy to factor.
So it would be the probability of finding a smooth element.
Yes.
But that doesn't tell you that the relation you sample in the lattice of relations your class group is random.
No, I'm not saying we can eliminate all the heuristic. I'm just saying we're having a new handle. That's why there's a question mark. It's big open problem.
You could hit the same relations over and over with a very, very well analyzed probability. Like if you get that probability of getting smooth elements, you would not necessarily know if you're hitting new relations.
No, but so I mean, it's not like we just apply the usual algorithm and do this. It's more like, okay, we're going to make the algorithm look uglier. We're going to do things that are not necessarily natural in a heuristic sense, but we're going to make it fit the theorems. So I'm not saying I'm taking your theorem black box and applying my magic and we're done. It's more like we have handles and we can modify a little bit the algorithms and tweak things in a way that make them not necessarily fully provable, but maybe more provable.
Okay, so we have 2 talks this morning, so I suggested that if we want any break between the talks, I suggest that we keep talking over there. Another announcement, so tomorrow's schedule, I noticed on the website, it has the wrong times. Tomorrow's schedule is going to be just like today, starting at 9:30 with 2 talks in the morning. The website is being fixed, but yeah, just to give you an early warning. Okay, so then let's thank Luca again. And we will resume at 11:30.
I get it twice.